Okay, this is lesson 2A, counting strategies often used in probability problems. When we have equally likely outcomes, that's actually structurally one of the simplest ways to compute probability, but many of those problems are among the most difficult to actually compute because it's so difficult sometimes to count the number of outcomes or the number of outcomes in an event. So what we're going to talk about in this video is 6 strategies that I believe are the most commonly used when we encounter probability problems. So we'll start with counting strategy number 1. This one is just listing out all the cases and simply counting them up. So if it's possible to do this, this is the best way of all to count something because it's the least error prone. If you can see a listing of all outcomes, you can be positive that that's the number. So for example, if we're trying to roll a dice one time and it has 6 sides to it, then the outcomes are 1, 2, 3, 4, 5, 6. We can simply list them, and then there are 6 outcomes. Or if we're drawing one ball from a box that contains 1 red, 1 blue, and 1 green ball, then there are only 3 possibilities, red, green, and blue. Those could be listed, and then we could just count them up. Sometimes you have something that's a little bit more involved, but you can still list everything as long as you use some sort of methodical procedure to make sure you've listed everything. Here's an example. Let's say that we're talking about finding probabilities related to children in a family. So a family has 3 children, and we want to know something about their genders in order. So there's a couple ways to be methodical about this. One way would be to keep everything constant on the left of our list and change things only on the right. So for example, we could say, okay, the first 2 children could be boys, and then the last child could be a boy or a girl. So we could list boy, 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 and then boy, boy, girl. And then we could say, okay, let's move back one level to the second child and change that person from boy to a girl, and then we'll again run through all the possibilities for the third child. The girl, it could be boy, girl with boy, and then boy, girl with girl. And then once we've got that, we can do a copy of that, except this time with girl being the choice for the first child. So girl, boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. And then when we count that up, that's a total of 8 possible outcomes there. Another way to do that same problem would be, let's list all the 3 boy families, and then list all the 2 boy families, and that means we have to pick the spot for the girl to be in. The girl could be last, or the girl could be in the middle, or the girl could be first. And then we could list all the 1 boy families, which means we have to pick the spot where the boy is. The boy is either last, or the boy is second, or the boy is first. And then we could list the no boy families, which there's only 1, all 3 girls. So that would be another way to list the 8 outcomes. So using some kind of a methodology like that. Another great way to make sure that you've got all the outcomes listed is to use some kind of a physical structure or picture or diagram to do that. For example, with the family children example, we could use something called a tree diagram that shows the outcomes here, right? The first child could be a boy or a girl, and then depending on what was chosen, the second one could be a boy or a girl, and then the third level could be a boy or a girl. So this proceeds from left to right, and then at the end, we can follow a pathway through the tree and see what the outcomes are. The top one is boy, 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 then boy, boy, girl, then boy, girl, boy, and so on, and we can count those end nodes of the tree, the leaves of the tree, and find out that there are 8 possible arrangements of genders of children. Or let's say we're trying to find something related to the sums of a roll of 2 dice. So one of the dice, maybe if it's 6-sided, could have the values 1, 2, 3, 4, 5, or 6. We could list that here on the top as a listing of columns here. And then for the rows, we could list out the possible values for the second dice. So that could be 1, 2, 3, 4, 5, or 6. And then in blue here, we've got the sums. So for example, this value right here, right, that value right there is a 6 because it's a 2 from one die and a 4 from the other die. So we can quickly see that there are 6 times 6 or 36 total outcomes here. Okay, so just to summarize strategy number 1, it's to list out all the cases and count them up. So we could either just do a simple set listing, or we could use a methodical procedure of some kind, or we could use some sort of physical diagram. All right. So the second counting strategy is called the multiplication principle. If you have multiple choices that have to be made, and each possibility for choice 1 can be paired with each possibility for choice 2 and choice 3 and so on, then you're allowed to use something called the multiplication principle. Here's an example. Let's say you have 2 pairs of pants, 3 shirts, and 2 pairs of shoes, and you want to know how many different outputs can be put together. So let's say you have jeans and shorts. That's your choices for the pants. You have a black shirt, a blue shirt, and a neon shirt for the shirts, and you have Vans and flip-flops for the shoes. So you could use a tree diagram and list that out methodically and then count them up. There's a total of 12 possible outfits here, so 12 possible outcomes, right? But even at this level, with 12 outcomes, it's pretty time-consuming to draw out that whole tree. Would there be a better way to do that? Well, to use the multiplication principle, what we do is we identify the choices that need to be made, and we write what I call a box, which is just a line that we can fill in with a number, a box for each choice that we need to make. So we're going to have a box, right, for the number of ways to choose the pants, right? We're going to have a box for the number of ways to choose the shirt, and then we're going to have a box for the number of ways to choose the shoes. Right? And what we'll do is we'll fill in those boxes with the number of ways we can make those choices. So since we have two choices of pants, jeans and shorts, that means we would put a 2 down here in this box, because there are 2 ways to choose the pants. There are 1, 2, 3 different ways to choose the shirt, so we'll put a 3 down there. Now, not 6, just the 3 actual choices. And then there are 2 ways, Vans and flip-flops, to choose the shoes. So we fill in each box with the number of ways to make that choice. Okay, the next step in the multiplication principle is we multiply the numbers in the boxes to get the total number of outcomes. So 2 times 3 is 6, 6 times 2 is 12, there's 12 outfits, 12 outcomes. And you can kind of see why that's true, because if you look at this case here, once we've made the jeans choice, we have 3 choices for shirts, right? But those 3 choices could have been chosen in 2 different ways. So it's 3 times 2 different ways to do that, right? That's why that first one would be 2 times 3. And that's why we want to multiply, because each of the second choice can be made the previous number of choice times. So that's why it's called the multiplication principle. So multiplication principle is great to use when there are too many outcomes to list or to make a tree diagram. Here's another example. Let's say that we wanted to find out how many different license plates are possible if you have 3 letters followed by 2 numbers. So to try to make a tree diagram of this would be prohibitive. There's no way we could possibly draw that out. But we could put a box per choice. We would say we have to make the choice of the first letter, and the choice of the second letter, and the choice of the third letter, then the choice of the first number, and the choice of the second number. And then we could fill those boxes with the number of ways to make the choice. There's 26 letters in the alphabet, so we'll put 26's in for the numbers of letter choices. And then there's 10 ways to choose the numbers. If we can use 1 through 9, that's 9, plus 1 more for the 0. So there are 10 digits that we could use. And then we would multiply those numbers together. It turns out there are 1,757,600 different license plates possible, which goes to show that there's no way we could have written this out by listing all possible outcomes or do a tree diagram. It would have almost 2 million different endnodes. So multiplication principle. We use this when the situation requires making multiple choices, and each possibility for choice 1 can be paired with every possibility for choice 2 and choice 3 and so on. And the way it works is we make a box for each choice, we fill in each box with the number of ways to make that choice, and then we multiply the numbers in the boxes to get the number of outcomes. Okay, counting strategy number 3 is called permutations. Here's another example that can be actually counted in 2 different ways. If 50 runners start a marathon, how many different ways can first, second, and third place be awarded if there's no possibility of a tie? So one way would be to use the multiplication principle that we just did. We can make 1 box per choice, so that would be a box for first place, a box for second place, a box for third place, and then we would start by filling in 50 for the first place, because until we know who's coming in first, all 50 runners are possible to choose to be first place. But once 1 runner has been chosen to be first place, that leaves only 49 runners left that could come in second. So the second number here is 1 less than the first. And then once we've used up a person for first place and second place, then there's only 48 runners left for third place. We would multiply 50 times 49 times 48 to figure out that there are 117,600 different possible finish orders. Okay, but this is actually a very special situation. It's a set of unique people that we can distinguish from each other, where we're choosing a person out of a set. And when we choose a person to come out of the set, that person gets used up. We can't choose that person again. That's a special situation. When we have a set of unique items and we use up items as they're chosen, that special situation is called either a permutation or a combination. And the difference between the two is if the order that we choose matters, if the first box and the second box and the third box are different in some way, then that is called a permutation. And if the order doesn't matter, then it's called a combination. So the formula for finding a permutation is this given right here. NPR is equal to n factorial over n minus r factorial, where n is the total number of elements in the set and r is the number of elements we're choosing. Okay, so this is the formula if we wanted to compute this by hand. Let's go ahead and use this formula, and we'll show you how you can use it. I'll also show you how it works on a calculator if we wanted to solve that same problem. We have 50 runners. We're choosing 3, one to be first, one to be second, one to be third. So order matters because there's a difference between first place, second place, and third place. So we could do this with a permutation. That means that the number of elements n is 50 because we have 50 runners to choose from. R is 3 because we're choosing 3, one to be first, one to be second, one to be third. So we're going to be computing 50p3, permutation choosing 3 out of 50. So that would be 50 factorial over 50 minus 3 factorial, which is 50 factorial over 47 factorial. And if you recall what factorial means, is it's that integer times every integer less by 1 until we get down to 1. So 50 factorial is 50 times 49 times 48 times 47 times 46, all the way down to times 2 times 1. And the 47 factorial is 47 times 46 all the way down to 1. But what that means is everything from 47 on down will cancel because it forms a 1, and that fraction can be removed, leaving 50 times 49 times 48, which is the same thing that we got when we used multiplication principles. Those are the values in the boxes. Of course, if we decided to do something with permutations, we usually wouldn't do the formula. Usually we'd use a calculator. So I want to show you how that works. If we're looking at, say, a TI-84 calculator, you can turn on your calculator, and you have to put the first number 50 first, so you'd select 50 here. And then if you go to the Math menu and you scroll over here to the PRB Probability submenu and you scroll down 1 to NPR, you select that, and then you put the 3. So 50 permutation 3 looks like this on a calculator, and you can get that 117,600 different first, second, third finishes in a single step. Okay, so a permutation can be used to count if you have a unique set of items and they're all identifiable, like they're distinguishable from each other. You're choosing some or all of these, and when you choose an object, it gets used up and can't be chosen again, and the order of the objects matters. Okay, let's take a slight variation of this. Let's say we have 600 seniors, and we want to make a prom planning committee of 3 seniors. How many different committees could be formed? This situation actually is the other one called the combinations, and we'll see why. Let's try to solve this using the multiplication principle like we did with permutations at first. First, we could ask how many different ways we could choose the 3 seniors, and we could use boxes. So we would have a box for the first senior chosen, a box for the second senior, and a box for the third. We'd have 600 seniors at first. 1 would get used up, so we'd have 599 left to be chosen second, and then 598 to be chosen third, and that would be about 215 million different possible groupings there. All right, but the problem is, let's imagine that the 3 people chosen were Alicia, Jack, and Lauren. Okay, so Alicia, Jack, and Lauren might have been chosen in that order. Alicia first, Jack second, and Lauren third. But it could have been Alicia chosen and then Lauren and then Jack, right? Or it could have been Lauren and then Alicia and then Jack, or Lauren and Jack and Alicia, or Jack then Lauren then Alicia, or Jack then Alicia then Lauren. But each of these would show up as a separate grouping in this 215 million number. But the truth is, all 6 of these are really the same committee, because it doesn't really matter what order we pick the people, they just end up in the committee. So that means we have 6 times too many committees being identified here. If we really want to find the number of committees, we need to divide that giant number by 6, so that all 6 of these count as the same committee. So there's really only 35,820,200 unique committees. So what about this 6 number here? Where does that come from, this 6 number? Could we figure that out without having to literally make up names and list them out? Well, what the 6 represents is the number of ways you could choose to line up the 3 people that were selected, that we did select. So if we made another set of boxes, where the first box was which person was chosen first, and the second one which was chosen second, and the third was which was chosen third, right? There are 3 names to choose to be in the first spot, and then one would get used up, and there would be 2 names to be used second, and then the 1 name left over. 3 times 2 times 1 is the 6. So that 6 that we're dividing by is really the number of ways to reorder the 3 people that we chose. So that's pretty darn complicated, though, so it's better if we can just identify that this situation is a combination and use a formula. So there is a formula for this. It's called NCR, C for combination. N and R mean the same things. N is the total number of elements in the set. R is the number of elements we're choosing, same as for permutations. There's a couple ways to write it. One way is NCR, like that with a C, and sometimes it's written like this, like with parentheses with the N on top and the R on the bottom. And it'll be read N choose R. Okay, so the formula looks almost the same as the permutations formula. It's N factorial over N minus R factorial, but then there's an extra R factorial on the bottom. That extra R factorial is the divide by 6 in the last example. It's dividing by the number of ways to permutate or arrange the elements that we select. So let's again rework this example, but this time we'll do it with a combination formula. So if there are 600 seniors and we want to make a prom planning committee of 3, how many different committees could be formed? We have a unique set of people. We're using them up, we select them. That means it's either a permutation or a combination. Because they just all end up on the committee, the order doesn't matter, so this is a combination. So we would use the combination formula. Out of 600 people, we're choosing 3. And that means that we would add 600 factorial over 600 minus 3 factorial times 3 factorial. If you put that in a calculator, or if you did it by hand here, that would be 600 factorial over 597 factorial, 3 factorial. And that means that, everything in the 600 factorial from 597 on down would be canceled off, leaving 600 times 599 times 598, and then divided by the 3 times 2 times 1, which is the same thing we did when we did it that complicated way with boxes within boxes. Oh, before we do that, let me show you that you can also do this in a calculator. You would do the same thing. We would say 600, go to math, and then over to probability, and the third item down, NCR gives the combination. We're choosing 3 out of 600 where order doesn't matter, and that means we have 35,820,200. All right, so in practice we would use a calculator for that. Okay, so a combination. That can be used to count if you have a set of unique identifiable objects. You're choosing some or all of these. When you choose an object, it gets used up and can't be chosen again, and the order of the objects chosen doesn't matter. So same as permutations, except that the order doesn't matter. Okay, only 2 strategies to go. Strategy number 5 is multiplication principle with combinations. There are some choices where we have to make multiple choices, but each choice is made by choosing a number out of a set. That actually happens fairly frequently, so I identify this as its own counting strategy. Often in these situations the order doesn't matter, so we can use a strategy that combines the multiplication principle to make a box for each choice, but then uses combinations to fill the numbers in the boxes. Okay, let's take a look at an example. Let's say that we need to make a committee, but this committee must include exactly 3 girls and exactly 2 boys. If there are 8 girls and 5 boys available who could serve on the committee, then how many different committees could we make? Well, sometimes having a picture of the situation helps. We start with the 8 girls and the 5 boys. They're just represented by G's and B's here. Okay, we need to choose 3 girls and 2 boys, but they each need to be chosen only from their own pool of the same gender. So we have to choose 3 of the girls out of the 8, and we have to choose 2 of the boys out of the 5. Okay, so we make a box for each choice, a box for girls, a box for boys. And then we fill in each box with a combination. So out of the 8 girls, we choose 3 of them. Out of the 5 boys, we choose 2 of those. And the reason it's a combination is because if I pick, let's say, Jill and Lauren and Melissa, it doesn't matter that I picked them in a specific order. They just end up on the committee. So it is a combination, not a permutation. And then finally, you would just evaluate those numbers. 8 combination 3 is 56, 5 combination 2 is 10. So 56 times 10, using the multiplication principle, there's 560 different committees that can be found. Okay, so you can use multiplication principle with combinations when you must make multiple choices and each choice is chosen from a separate set of objects. Just make a box per choice, fill each box with a combination, choosing that number out of the matching set, and then multiply. Almost done. There's only one more main strategy here. It's called distinguishable permutations. In all the previous examples, every item in the set was unique. But what if some of the items are repeated or are indistinguishable from each other? Let's compare the following two examples. In example 10, we'll say, given the following set of letters, how many ways can you rearrange the letters to make unique words? And we'll use the letters L-E-M-O-N. And in example 11, we'll do the same thing, but with the letters from the word banana. So if we want to do the case with 11, here we have a set of unique letters, and we're going to choose some or all of them actually, to make a word. When we select a letter to be included in the word, we use up that letter, and because different order of letters makes a different word, then the order does matter. This meets all the criteria for permutation. So we're choosing all 5 out of a set of 5 letters. So we would say 5, P5, and that turns out to be 5 factorial over 0 factorial. 0 factorial is defined to be 1, and that means it's just 5 factorial. So it's 5 times 4 times 3 times 2 times 1, which is 120. We could also have used the multiplication principle. We have 5 choices to make. We have to pick the letter for the first spot, the letter for the second spot, and third spot, and fourth spot, and fifth spot. All 5 letters are initially are available for choice, right? But once we choose a letter, there's only 4 left to make the second choice. The third letter can be chosen from the remaining 3, and so on, and we multiply those out. That also gives us 120. So either from permutations or from multiplication principle, we can find that there's 120 ways to rearrange the letters in the word lemon. Okay, so note, by the way, that this is a special case of permutations. If you are selecting all of the items to line up or rearrange, the number of ways that can be done is just n factorial. We can even identify that as kind of an extra little strategy, n factorial ways to line up all n objects, if they're distinguishable. Okay, but in example 11, the situation is different. We have the letters in the word banana, right? But the n's and the a's have more than one symbol that are the same. And that means that we could rearrange them, and in some cases we'll get another word where the letters have been swapped, but we won't be able to tell that that's happened. To see what's going on here, I've color-coded just the A's, one blue, one red, and one green here, so we can kind of see them being moved around. If we did a permutation like we did in example 10, then every different rearrangement of the letters would count as a separate word. Each of these would be considered separate words, but right, they're really not the different words, because if I didn't have them color-coded, they would all be the word banana, so we wouldn't be able to distinguish between those permutations, right? Okay, so we need a different strategy, and here's one we could use. Instead of choosing which letter to place in each position, we can use we can choose the positions for each type of letter. So we can say, let's have a box for the number of ways to choose the position for the B, and then a box for the number of ways to choose the positions for the A's, and then a box for the number of ways to choose the positions for the N's. So if we started with all 6 positions in the word open, we can choose one of those positions to contain the B. There would be 6 choose 1 ways for that to occur, because we'd have to choose one of the spots to contain the 1B out of the 6. So here's an example. Maybe we choose the second spot here to have the B. Okay. Now we need to choose 3 of the remaining 5 open spots to get the A's, right? We've used up 1 for the B, so there's only 5 spots left. That's why this is out of the remaining 5 spots, we have to choose 3 of those to contain the A's. So for example, maybe the A's are in the positions down there. This is just one possibility that I'm showing on the bottom here. And then we would want to choose positions for the N's, so there are 2 remaining spots, and we'd have to choose both of those. So choose choose 2 different ways to choose the positions for the N's. By the multiplication principle, we would figure out the combinations and multiply and get that there are 60 distinguishable words possible. And that's a perfectly good way to do this problem using the strategies we have. Even though we use combinations along with multiplication principles to count this situation is actually called a distinguishable permutation problem, because it's about the number of ways to order things which are not all distinguishable. So there is actually a special formula for computing this in a single step. Let's develop it using the example we just did. We had a total of 6 letters. There was 1 B, 3 A's, and 2 N's, and we ended up with this way to compute it. 6 combination 1 times 5 combination 3 times 2 combination 2. So if we were to write out the formulas for each of those combinations, we can derive this special formula. Okay, here's the first thing. If I just write out the combination formula for each one, 6 combination 1 is 6 factorial over 6 minus 1 factorial times 1 factorial, and so on. Same thing for these others. Those are just the combination formulas filled in. And then that means this is 6 factorial over 5 factorial times 1 factorial times 5 factorial over 2 factorial, 3 factorial, and so on. But since they're really being multiplied, you could really think of this as one big fraction. The 6 factorial, 5 factorial, and 2 factorial are on the top, and all the rest of these things are on the bottom of the fraction. A 5 factorial times a 1 factorial times a 2 times a 3 times a 0 times a 2 factorial. Okay, notice though that there's always going to be certain cancellations. This 5 factorial on the top here that I've marked in blue is always going to match up with this 5 factorial down here because they're both that number less out of the open slots. And the 2 factorials cancel the same way, and the remaining one will always be 0 left. And that means at the end we'll always get something like this, where the top number is the total number of symbols, and the bottom number is the number of each of the individual subsymbols factorial. So the result is 6 factorial, which is the total number of symbols factorial, and then the number of each symbol factorial. So that result, which is based on the way we analyzed it before, is written up as this formula. The number of distinguishable permutations is n factorial over n1 factorial times n2 factorial times n3 factorial, and so on, where n is the total number of objects, n1 is the number of type 1 objects, type 2 objects, and so on. All right. So, I know we've covered a lot in this video, but out of all the different ways to count, I think these 6 strategies are the primary ones that are used in probability. So if you kind of print this one screen out and keep it as a guideline, you should be able to find a good strategy on this list. Let's go over them again really quickly to summarize. Right, the best strategy of all is to list out all the cases and just count them up. You can also use tree diagrams, grids, methodical listing. This you should use. It's the best strategy of all, but you can only use it when you have small numbers. Multiplication principle: 1 box per choice. Fill in the box with the number of ways to make the choice and multiply. You can use this when you have multiple choices to make, and every possible choice in each box can be paired with every other choice. We have permutations, which we'll typically use a calculator for. A special case is if you're choosing all, you can know that's just n factorial. That's when you have a set of distinct objects with no repeats. You're choosing some or all of them, and the object are used up as you choose them, and the order matters. We do a combination if the order does not matter, but otherwise the same conditions as for permutations. We can use multiplication principle with combinations when you have multiple choices to make, but each is a choice out of a number of items out of a set, like choosing boys out of boys or girls out of girls, that kind of thing. And then the last one is distinguishable permutations. We have the special formula. That's just when we want to find the number of ways to rearrange all the items in a set if there are repeats, right? So that's a summary of all the counting strategies that we have, and move on to the 2B lesson, and we'll see how we can use these strategies to find probability of equally likely scenarios.